Have you ever wondered what is going on beneath the Earth's surface? Do you think that there's nothing below our feet besides dirt and worms? If so, think again. Today, we are going to learn about how dynamic and how active the Earth is underneath its surface. First, we are going to learn about the principles of plate tectonics theory. The theory of plate tectonics proposes what modern scientists believe is going on underneath the surface of the Earth. Then we will discuss the movement of large slabs of rock known as tectonic plates, dozens of miles below our feet. Finally, we will learn how the movement of tectonic plates can be seen and experienced on the Earth's surface in areas known as fault plains. According to the theory of plate tectonics, below the grass and soil that we can see, the Earth is composed of multiple layers. The Earth's outermost layer is known as the lithosphere, which is composed of the Earth's crust and upper mantle. The crust can be thought of as the skin of an apple. It is the Earth's outer shell. Composed of rocks and soil, the lithosphere is about 25 miles thick underneath the continental surface and 3 to 5 miles thick underneath the ocean floor. Within the crust reside nearly a dozen massive slabs of rock known as tectonic plates. The tectonic plates fit together within the crust to act as the outermost cover of the Earth's interior, much like the skin of an apple. These plates move extremely slowly within the lithosphere, and sometimes only centimeters per year. According to the theory of plate tectonics, there are more than a dozen of these plates located within the lithosphere. These plates basically fit together like puzzle pieces, but are constantly moving in slow motion. When these slabs of rock bump into, move away from, or grind against each other, it can have serious consequences for all of us here on the surface of the Earth. Tectonic plates can be found underneath the Earth's surface, continental plates, or below the surface of the seafloor, oceanic plates. The area underneath the crust is the upper mantle, which is a place much warmer and more active than the crust. The upper mantle represents the region between the extremely hot, soft lower mantle and the cooler, dirt-filled rock crust. Due to the extremely hot temperatures within the lower mantle, soft magma-like material rises up into the upper mantle, where it is cooled when coming into contact with the cooler material located in the crust. The rising and falling of soft magma-like material created by this heating and cooling process causes the upper mantle to be much more active than the crust. Since the crust rests on top of the upper mantle, this instability is the reason why the tectonic plates within the crust move around ever so slightly. Because the crust is composed of nearly a dozen of these massive tectonic plates, the plates are bound to bump into or rub alongside each other from time to time. When this occurs, large-scale geological activity is the result. As we will see, earthquakes, volcanic activity, and even large bodies of water such as oceans are created from the movement of tectonic plates. The movement of tectonic plates is most commonly described and classified by the boundary created between two plates as a result of their movement. There are three different classes of tectonic plate boundaries. The first type of plate boundary is known as a convergent boundary. Convergent boundaries are created when tectonic plates move toward each other. Plate convergence may involve two continental plates, two oceanic plates, or one of each. When two oceanic plates or oceanic and continental plates collide, the denser of the two plates will dive underneath the other where it is consumed by the Earth's interior. This process is known as subduction. Because oceanic plates are denser than continental plates, they will always subduct upon convergence with a continental plate, creating a subduction zone. When the subducting plate dives deep into the Earth's interior, molten magma is created. Over time, this magma oozes up through the crust and the Earth's surface. As a result, a chain of volcanoes are often created through the process of subduction during tectonic plate convergence. However, when two continental plates collide with each other, subduction does not take place. Rather, in a process known as continental collision, the converging continental plates become welded together to form one larger plate. When two continental plates collide, mountain ranges such as the Himalayas are created as the smashing together of plates creates compressional stress on the rocky slabs and causes them to move vertically. An analogy for convergent boundaries would be a head-on collision between two moving vehicles. Just as head-on collisions create substantial damage, convergent plate boundaries often result in the strongest of earthquakes. Earthquakes are measured on a magnitude of 0 to 10, with 10 being the greatest strength. Earthquakes created by convergent boundaries can reach a magnitude 9 and can occur at a subduction zone or at the site of continental collision. The second type of tectonic plate boundary is known as a divergent boundary. Divergent boundaries can occur in areas where two pre-existing plates move away from each other, or in an area where one tectonic plate is being pulled apart to create two separate plates. In a process known as rifting, rising currents of pressure within the Earth's lithosphere pull apart and tear the plate into two or more smaller pieces. The movement of rocks away from each other result in what is known as tensional stress. Tensional stress flattens and spreads rocks out horizontally. Once a plate has been rifted, the resulting smaller pieces may continue separating from one another by a type of plate motion known as divergence. When this occurs, molten magma material rises into the fractures between the rifted plates where it cools and solidifies, attaching itself to the edges of the rifted plates. An example of this process occurs when what is known as seaboard spreading. As oceanic plates move away from each other, this results in openings in the ocean's surface. These openings are filled with liquid magma, which cools and hardens, the result in the extension of the ocean floor's surface. Divergent boundaries can also occur outside of the ocean, such as when two continental plates are moving away from each other. For example, the continental African and Arabian plates created by a divergent boundary that is filled in ocean water. This resulted in the creation of the Red Sea, a relatively recent development according to geological history. If these two plates continue to move away from each other, the Red Sea will become the size of an ocean. Divergent boundaries can result in earthquakes of a magnitude 8 and lower. The third type of tectonic plate boundary is known as a transform boundary. These boundaries are created when two tectonic plates grind alongside each other. The movement of two plates grinding past each other in opposite directions is known as a transform motion. As giant slabs of rock slide past each other in these parallel opposite directions, the slabs are subjected to stress known as shear. Because the tectonic plates are rubbing alongside each other, neither of the plates experiences any substantial amount of growth or destruction. However, the edges of the tectonic plates become grinded up as the plates slide alongside each other. An example of this process is the creation of valleys on the Earth's surface as the rocks are grinded up and fall downward between the two plates. Along transform boundaries, earthquakes of a magnitude 8.5 and below are experienced. An example of an area where a transform boundary has occurred would be the San Andreas Fault, where the North American and Pacific plates grind alongside each other. Tectonic plates are the single biggest masses moving around within the Earth's crust, but they are not alone. Within the crust also lies fault blocks, which are large blocks of rock created by tectonic and localized stresses within the crust. Fault blocks are not tectonic plates. Fault blocks are created when large chunks of bedrock are fractured by stresses within the crust. Most of the stresses placed on fault blocks are a result of tectonic plate movement. For example, as a tectonic plate moves forward, it compresses the rocky material in front of it, which applies stress to those rocks. When stress causes a fault block to break or fracture, its effects can be seen and experienced on the surface of the Earth. As plates move, they cause fractures in the rocks known as faults, and the area where these fractures occur is known as a fault plane. Fault planes are the surface along which movement between two fault blocks occurs. There are two different classes of fault planes: dip-slip faults and strike-slip faults. Each of these types of faults is distinguished by the way the fault block moves in relation to another and how they move from their original positions. Along any fault plane, there are two types of fault blocks: the hanging wall block and the footwall block. fault blocks represent sections of the rock within the Earth's crust. The hanging wall block is the segment of rock that was closer to the surface of the Earth before the slip took place. The footwall is the segment of rock that was farther away from the Earth's surface before the slip took place. The term slip refers to the fact that movement between the two fault blocks took place. The movement of fault blocks along a fault plane is defined by the vertical movement of blocks, known as the dip, or the directional orientation of the horizontal crack on the Earth's surface, known as the strike. So, dip-slip faults are created when two or more fault blocks move in a vertical direction relative to each other. Dip-slip faults result in an inclined terrain. For an example of a dip-slip fault, consider two people standing right next to each other. If a dip-slip fault were to occur between the two of them, one of them would end up at an elevated position relative to the other. Strike-slip faults are created when two or more fault blocks move in a horizontal direction relative to each other. Strike-slip faults result in the original terrain being offset horizontally to the left or to the right. For an example of movement along a strike-slip fault, imagine two people standing one behind the other. If a strike-slip fault were to occur between them, you would see the last person in the line shifted to the left or to the right. There are two types of dip-slip faults, normal and reverse faults. Normal faults are created when the hanging wall moves downward relative to the footwall. This type of fault typically occurs when fault blocks are moved as a result of divergent tectonic plates beneath them. In a normal fault, the hanging wall moves vertically downward in relation to the footwall. In order for this to occur, tensional stress is required to pull the rocks and stretch them horizontally, flattening them out and bringing the hanging wall down closer to the footwall. This is called a normal fault because it is similar to what you would expect from the law of gravity. What was on top was pulled downward. The second type of dip-slip fault is the reverse fault. Reverse faults are created when the hanging wall moves upward relative to the footwall, or the reverse of what you would expect given the law of gravity. Reverse faults typically occur in areas where two tectonic plates are creating compressional stress as they converge. To make the hanging wall move upward, this powerful compressional stress is required. This stress squishes the rocks and forces them to extend vertically upward. Returning to the aforementioned strike-slip faults, these are formed by a horizontal slip of adjacent blocks of rock. That is, each fault block on either side of the fault plane moves parallel to each other, like two trains running alongside each other headed in opposite directions. Strike-slip faults typically occur in areas where tectonic plates are grinding alongside of each other, creating shear stress resulting in a transform boundary. The result of a strike-slip fault is that the features on the surface of the Earth that reside across from the fault plane are offset laterally or sideways. Strike-slip faults are classified as either left lateral or right lateral faults, depending on the sideways movement of the surface features. For an example, pretend that you are standing 100 yards away from a barn and a strike-slip fault occurs between you and the barn. If after the fault occurred, you are standing in your original position and the barn shifted to your left, then a left lateral fault occurred. If the barn moved to the right, then a right lateral fault occurred. Now you know a little more information about all of the action that is going on underneath our feet. It may have come as a surprise to you to know just how active things can be underneath the ground that we live, play, and work on. The Earth is an active, interesting place. The theory of plate tectonics and an understanding of fault planes show us just how active and interesting it really is.